So this will be laboratory work number 5, which is called coherent demodulation of AM signal. And just I'm trying to look if there is a description already loaded. No, description is not here. So let's check. So this is coherent detection. Okay, I have to translate it. It doesn't exist in English. So, okay. This is not a big deal. Maybe I will start with some simple explanation, and this will be just partly already was presented in the last lecture, which was like a couple weeks before, when we was talking about the PLL. And what we wish to do in the next lab work, we will use PLL for the demodulation of amplitude modulated signal. So we will use not this magnitude detector, which we was using in laboratory work number 3, yes. We will remove this and replace it with PLL, which will do the same job, but it will allow you to better tune and achieve better quality of the signal. I believe it must be so. However, it will be at cost at much more complex system. So let's check if the recording is active, because now this is essential that when you will do laboratory work and you will try to, maybe you could try this at home or do it remotely in the class, but
good afternoon, Professor.
Yes. Do you have a question?
Yeah, no, Professor. I just like to wish you.
Okay. Hello.
Hi.
Okay, let's talk little bit some basic ideas. So essentially, maybe if someone remember laboratory work number 3, I think it was number 3, all this numbering. Yes. In number 3, we were doing like this. We had this a down Pluto receiver. Yes, this is a Simulink, what we did in Simulink. We are not talking about some hardware blocks now. And here, after down Pluto, we had some bandpass filter. If you remember, it was from like, it was centered about 40 kilohertz, so it has some 40 kilohertz center frequency, and it was like this, and starting from 20 until 60, and here was like, I think 30, and here was a 50, something like this. This is not this bandpass filter. And after the bandpass filter, actually we had this magnitude detector. This is just was this block which was extracting magnitude from the complex variable. In this case, it was a complex signal. And for example, if you had something like this, then this magnitude detector was extracting this value, because actually because of the phase shift, it happens that it will extract this envelope of the signal. Yes, because it will take two. In fact, this is, if we look to the signals, that it will be like real part and an imaginary part, little bit shifted in the phase. And because of this, the magnitude goes a straight line, not like if you had only a real part, that we could have something like this. Yes, just we will extract magnitude, but this is not the case if you have real and imaginary part. This line doesn't have this yellow doesn't have these jumps anymore. It just goes straight line. And I have seen this into your lab works, and this is correct. And then we just, this demodulated audio signal have sent to the speaker. Yes, it will be audio output. And we were able to listen the radio station. Of course, I was running the transmitter somewhere, which was transmitting signal, but you will be doing also on the receiver in this P05 also. So the actual, this amplitude demodulation was happening into this block. Yes, this was block which was doing this AM detection, because this bandpass filter is only auxiliary function to avoid noises and increase this signal to noise ratio, because you do not need to demodulate all signals coming from this in this band. So you just need this audio modulated, this amplitude modulation radio station. In this case, bandpass filter always helps, and it's always necessary to use these bandpass filters if you wish to increase sensitivity of the receiver. And only problems that good bandpass filter usually requires a lot of components, and if it is hardware bandpass filter, and if it is software like digital filter, they'll require anyway a lot of computing resources to get like relatively flat this part, because if you have not flat this part, it will also change the spectrum of the audio signal which is played back, and this is not a good thing. So what we will doing in the next laboratory work, P05. In P05, yes, what we will do. We will use our PLL, which we were constructed in P04. And instead of this block, we will put PLL. But this is only roughly speaking. That's why I'm not drawing it, because actually we will use PLL for the demodulation, but actual demodulation will be done by some simple multiplier. And here we have this exactly 40 kilohertz generator. So our generator will be tuned exactly to the middle of this signal. This is very important because if you tune exactly to the middle of this filtered signal, then you will receive at the end here also this yellow shape, yes, and because you will down convert, you actually will do down conversion from 40 to 0 hertz. So you will down convert using this multiplication here so that it will be exactly 0. But it must be exactly 0, because if you have even like 100 hertz offset here, not 40, but something like, and actually your radio station will never have center in 40, it will have like 41 or something like this, because you will be tuning all the time and your tuning window will be like something like this. And okay, no, maybe okay, maybe it's not correct to draw like this. It's better to show like your radio station is somewhere here, yes, within this band of the filtration. And after down conversion, you must have this exactly in the middle, even if it is not in the middle in this pass band, yes, but it must be in the middle. And of course, then maybe this, if we wish to be correct, then maybe we could also draw that our filter will be a little bit, but anyway, this filter will not be present at this 0, because after down conversion, we will not have any other things. Maybe the presence of noise in this some kind of band where filter exists will show you some track of this filter, yes, and no noise outside this band, but because it will filter also the noise, yes, here. And in logarithmic scale, this is clearly visible, such kind of some platform here at the bottom of our useful signal. And the main problem here is how to get exactly in the center of this transmitted signal. This could be relatively easy for so-called AM, DSB, TC. Yes, this is transmitted carrier signal. What does it mean? It does mean that in the center of the spectrum, you have huge peak corresponding to this carrier. And then it is with PLL, it's possible we will use the signal itself for the driving of the PLL. So what we will do, we will derive this signal itself, send to PLL, and this PLL will drive this oscillator. Actually, this oscillator will be separate oscillator, because inner oscillator will have this, like, if you remember the last lab work, we have introduced second VCO. And this is this second VCO, in fact, yes, this which we had. And this is the first VCO, which will be part of this loop. And this second VCO will be this, and it will generate this signal. exactly at 40 kilohertz. And like it will happen when immediately when some of the station will be in the bandwidth of filter and also in the band of PLL automatic tracking. Yes, you remember that last time you could have quite big offsets like 10 kilohertz, or no, okay, it was hertz, like if you had this 100 hertz center frequency and we could offset even 10 hertz. So in this case, it could be like, if it is 40 kilohertz, we could talk about like 4 kilohertz offset here. So that even this offset is 4 kilohertz, the PLL will tune this oscillator so that it will become in the middle, because we will be synchronizing to this internal oscillation of our amplitude modulated signal. And for the AM/DSB/TC, this is relatively easy because you have this very big carrier in the middle. And then you will even hear this sound, this tube, when it gets tuning to this, exactly to this frequency, and then you will have very, very clear sound and so on, because it will be exactly tuned to the frequency of the signal, and also it will be tuned to the phase of the signal, so it will maximize the reception as much as possible, because phase of this generator will be exactly as phase of incoming signal. Here, of course, we could think about, because we need only one part, or either real part or imaginary part, and then we will have to decide which part to use here. And as much as I remember, in our laboratory work, we will use the real part, yes. And so we will have here some block which will extract the real part, because we need only one signal. We cannot use complex signal in this loop. That's why we install this real block and use only real part. Actually, there PLLs which use complex signals also exists, and we also have even laboratory work for this, but this is quite heavy, and last semester students was quite struggling to do it, and then I was thinking that maybe we'll skip this laboratory work with complex PLL. In fact, this is two PLLs, so-called Costas loop, and it's possible then not use this real part and synchronize to both, this blue and green, but then it's much, much more complex, and also much more require much more tuning, let's say. And students, some people was not even able to run it and disappointed, and well, not easy. So actually this PLL inside will have, of course, all this structure. So actually that means that will have this phase detector, which will connect it to this VCO. Yes. And here is this loop filter, and it will come to the loop filter. So, and from the loop filter, we will also have second signal which goes this way, and this is this. This will drive this second VCO as well. So it will drive both this first VCO and second VCO, and then it will be able to work. And now we will try to build this in real life and check if it is working, to pay some attention. But in fact, we can use this ready PLL, which we already had done. And of course, yes, I just forgot to mention that here we need also this low pass filter, because mixing will produce this double frequency component as well. So this is low pass filter, and then it will go to the audio output. There is also sample rate converter in this point, but I don't draw it because technically it's just some auxiliary element which not principally important for this structure of coherent. This is so-called coherent detector. Why it's so called? Because coherent, because those generators, this generator is in phase and frequency exactly synchronized to the incoming signal. So it will have, and this is called coherent detection. Coherent means that phase, actually this phase is taken into the account. Okay, maybe we could try to run this. I just now thinking that we had two choices. We can run on my computer, in the classroom computer. But okay, let's try on my computer, and then on next week we will try to do this on the classroom computer, because the Simulink versions, of course, are a little bit different, and it will impose some, at least visual differences. But anyway, I think you should understand these differences, at least this, because anyway, you will be in the future, will be dealing with newer versions than there is in the classroom. And maybe believe some people already have, like us, still have installed newer version, not this 2018. Okay, I will run some, today I will try some interesting thing. I will try to access remotely one computer, which is not in the internet, but here staying beside me, because running the Simulink together with Zoom is quite painful. Okay, let's try if it does connect. Okay. Share. Okay, you see it, yes?
Yes.
Okay. I use software called NoMachine. This is also some kind of remote access software. I don't know if it's much better than any desk, but I like it. But it doesn't allow, I think that it doesn't work behind the firewalls. So any desk is more powerful in this term. And also I haven't switched this machine. Okay, but maybe I was switching it on Sunday. I was just afraid that it will start update everything because I haven't used it for a long time. Okay, I will run the Matlab. Okay, but this is some problem because I need to get the files. Just thinking I will need some way to copy the files. It doesn't support maybe because any desk was have some this very nice feature of recording connection devices. What is this? Connected, disconnect USB device, connect network port, smart card readers. Oh, very good feature. So I can connect disk on my local machine to this remote machine. Like SD. What will happen?
It is loading, Professor, there near SD.
Sorry?
It is loading near SD, right?
Yeah, just it looks like
Something happened. It's like warning symbol is happening there near the SD.
program tried to new system extension. Okay, this is kind of, I need to allow to access my disks. Okay, let's check. Because I need to transfer models from the previous laboratory works. General details, NoMachine. Okay. Okay, it requires restart of the machine. Oh no. Okay, then I will use a flash drive, which I will just plug into my machine, and then we'll plug into this another computer, because I have to somehow transfer the files. However, I don't like this flash drive thing because it could have a virus, so I will. But how can I do else? Restart of the machine is not interesting. Anyway. Okay, how we can do this? Interesting. Data machine remote disks. Okay, but if I connect to remote disk, for example, to C, or no, E, for example. Users, authors, E. The directory doesn't exist. Okay. Not that easy. E. E. The directory E doesn't exist. It removes this directory actually because to create the directory. Yes, something goes wrong. It doesn't work. Unfortunately, this tries, but then it goes to error directory edisk doesn't exist. However, this directory actually is deleted. This is really strange, but deletes this directory. Okay, local other. Okay, what we could do now. Let's see, maybe see. The same issue we see as okay, let's check if this computer has something connected. Maybe it just shows warnings, but still. Oh, I have a great idea. I can use OneDrive for the exchanging of the file. Okay. This is only itself. Okay. I will just put the files to the OneDrive. What I will need Simulink model for the P04 PLL. And I also will need this P03 IM okay, these two files. Okay, let's use it. Sorry that I was a little bit doing something and you had to wait. So I will just put these files to the OneDrive. I will put somewhere to temporary. Okay, I will just put to the folder of the course, for example. Because I do not like really putting Simulink to the OneDrive, because OneDrive gets synchronized all the time. And that means all these temporary files, which will be created during the compilation, will be synchronizing all the times forth and back over the network. And this is completely not good. But I put it just for the exchange. I will not run them from the OneDrive. Copy. Then I will put also this IMDSD. But oh well, we need also the transmitter, and this could be difficult to organize. Okay, anyway, I will have to run the transmitter, but then I will need also two software-defined radios. And here at home, I have only one. And without the transmitter, it could be not possible to check if it is working. That could be a little bit not interesting at all. But okay, we was in the last year, we was doing such a also hack that we was running the transmitter on the same Pluto where we had the receiver. It's also possible, by the way. You can run, you can put the transmitter and run the transmitter at the same time as the receiver, and transmit and receive from the same unit. So of course your antennas will be like maybe apart few centimeters, and also in the classroom I do not have, okay, I have also antennas connected in the classroom. You also do this also, but this is not that interesting, because if you run it from the same Pluto, the frequency synchronization will be perfect between the transmitter and receiver, because they have used the same oscillators internal. So, but okay, we will use this is the model which we was using last year. TX Pluto. Maybe this. Receiver Coherent. Okay, and we will need this envelope receiver because we will use it as a reference. Okay. Okay, what you see now, you see this Windows still, yes?
Yes.
Okay, then I will go to the OneDrive, and it must be models, and they are okay. Nice. Now I will copy this to the desktop to avoid compilation into the OneDrive folder, because it could be okay. Now we will start, because we will not build it from the scratch. We will start with a model of laboratory work number 3. Now we will choose wow, why it's Russian. Users, it is like AA, desktop, models. So we have this envelope receiver model. And I will go and create some software-defined rate while it's lunch. Just thinking that I will need a driver for this as well. Okay. Let's check if Matlab has a driver. Add-ons, hardware support packages. Yes, here you should check if you have support for a down Pluto in this Matlab. Yes, here communication toolbox. You could install this. This is relatively easy. Install. Here you should log into the MathWorks, even if you have some kind of version which you have not purchased. You could register in the MathWorks. It isn't a problem at all. You just create one and go on. let's try to guess the password. Accept. Next. Hopefully it will install the fastly. In this aspect, this Matlab is very good that it installs all the drivers automatically, because in the other software which we will be using, this GNU radio, this is not that simple at all. This is a lot of pain, and I think many people will not be even capable to do this work, because it requires some command line actions and searching in the internet and so on. Here the process is quite smooth, and usually it works very well. And it also works on Windows, Macintosh, and Linux the same way. This is also very good. Test connection. Now it should show actual data from the device. Okay, it works fine. We don't need examples. Okay. Okay, fine. Let's go back. Now we will go to our models. This is our receiver model. And now this block must be running. If I run, it should fix this red. Okay, now, of course, because we do not have a transmitter, this is just a noise which is amplified by the filter. This is what I was talking in the beginning of the lecture, when I was drawing that filter cuts everything outside this band where it's amplified. So it has like 40 kilohertz bandwidth, and it's centered exactly to 40 kilohertz. Now you see the center is approximately at 40 kilohertz, and it goes from 60, actually from 20 to 60. So bandwidth also is about like 40 kilohertz. And it amplifies the noise. Yes, that's why you have this signal here, although we do not have any transmissions yet. Yes, and now what we will do, we will add some transmitter here, because otherwise there will be no way to check it. In your lab work, just I'm thinking that if we, this is my fault that I haven't taken second Pluto with me, because we have plenty of Plutos not used now, but I haven't taken. This is a big problem now, because now we will have to leave. We will use a local transmitter, which I will just put into the model. You will not have to do this, because you will have a separate transmitter and you will make only a receiver. So what I will do now, I will open model of okay, maybe let's go from the Matlab. Here I have a transmitter. And I will just copy it to my model. Okay, I will need much more space, of course, due to this problem. Maybe I will. And this tuning, of course, in this case, it's not necessary because I already said, because there is no frequency offset, because this is the same unit. I can just exactly tune to some frequency. It's interesting that I cannot delete the slider. Okay. Delete. Put the transmitter here. Of course, I will little bit simplify it. I will remove this switch. Connect here. Okay, we need a multimedia file as well. Okay, but maybe we will not use multimedia file, but we will transmit this single tone. Why not? So it will be just single tone transmission. Okay, here I have to set the same frequency in the receiver and transmitter, 433.3. And this is 433. So this will be, we need like 0 dB gain, because we could easily overload now because we have two antennas staying beside each other, and this could be a problem. Now we could run. Okay, here we need complex signal. What we could do, we could just make it complex. Here we could do dirty trick, just plus EPS J. That means that it is very small imaginary part gets added to the signal. And that's now it will become complex. Okay, now baseband rates are different. 480, 240. Okay, let's use same rate here. but we also should use it here as well then. So we have to adapt the transmitter to the receiver model because I do not have two Plutos. But I will show that it's possible to run the transmitter and receiver at the same time. Okay, what I see is that now it's completely overloaded. So I will reduce gain by minus 60 dB. Oh, that's funny at all. Oh, what's going on? Doesn't work. Okay. Automatic gain control. Okay, now it's more or less okay. This is a spectrum. DC blocker. We have now even some kind of signal, but I do not believe that we have any sound, but I do not hear anything. This is a because I think that it blocks the sound. Audio. So it's not that easy. Seems that I overestimated because seems like sound is not coming at all. But okay, let's skip the sound thing. Let's go with what we have to do in the laboratory work. So actually we have to increase a little bit power of the transmitter. Now it gets overloaded already. Oh no. Okay, minus 50. Maybe let's remove the antenna from the receiver at all, because I think it gets overloaded anyway. Minus 30. Because transmitter signal is too weak. And that's why we do not see any useful signals at all. It's very strange. It looks like a noise. This is a sine wave, 500 hertz. Okay, let's use like 5,000 hertz. Okay. Yeah, this is a tuning problem because this is, you have the same transmitter and receiver, and it requires some tuning to get it working, but it seems like we can barely guess. Receiver is too weak. Let's increase by 30 dB. Four 33.3, 0.33.3. Okay, let's last try. If it will not work, okay, there is some signs. You see, those two peaks actually are, they are our 5 kilohertz signal. Okay, it's somewhat working, but not that well. But we would be able to hear it if we would have sound. But okay, let's skip this part because we will need to finish this PLL thing and then we will go today. Okay, what actually you do now? You will not put this transmitter. You will go from this point if you have this laboratory work number 3 file. What you do actually, you just go and remove this DC blocker and this amplitude detector. Okay, the next thing what you do is go to laboratory work number 4, PLL. And you see, this is our PLL, which we were using in the previous laboratory work. What is this? Something funny, never have seen this. Copy this over. Just copy and go to our receiver. Maybe a little bit decrease the dimensions because now it will require some space. Okay, I will have to zoom it. Wrong. There's too much windows already. I will maximize this. And I paste this PLL. Yes. And there is why those blocks are red, because you are missing those parameters, because those parameters was calculated into this script, which we were using and which we will need to run this PLL. And so that's why you will need also this PLL init script. And I have copied it over. And now I have to copy it here as well. PLL init script, which is also what is important, that before you run, you need to put the right parameters, because now the carrier frequency is not 100 Hertz, and this PLL is not connected to your student ID, because now you have a center frequency which is related to your student ID. But in this laboratory work, we will use frequency which is 40 kilohertz. Only thing which is different for each student is this damping ratio, which will be again this A.BC, yes, and this is only thing which will be different between the students. So if you have a script, yes, if you have a script, you could modify it easily. Yes, for example, I have this PLL init script. I could just go and say that now the sample rate is fixed. It's just 240 kilohertz, because this is a band, but our sample rate in the model. Quotient frequency must be 40 kilohertz. And again, this damping ratio must be dependent from your student ID, this zeta, and bandwidth will be 1 kilohertz, just also fixed. So if you have a script, you can run it and you will get all these values of the K1 and K2 actually, and also this B, and also which are used within this VCOs. And now those blocks, if you now run the model, they should not be red anymore, but we will not run yet because we haven't done all connections. So now instead of this sine wave, which was a reference in our previous laboratory work, we will feed actual signal from the receiver. So we will just connect the receiver Pluto output after the bandpass filter to the PLL. Maybe we will remove this scope because it will overload our system. But no, maybe we'll leave for a while because it's very good for the demonstration. And now this second VCO output goes to another mixer here. So we will install some multiplier. Here we go and install some product block. To the one input of the mixer, still this will go this signal from the receiver, from the bandpass, which also goes to the PLL. But again, it will, maybe I will put those blocks away from here to reduce this clutter. So now we have signal before the PLL, before the VCO. This is the first output, which goes to the loop, and this is the second output. And the second output will go to the second VCO, goes to this mixer. Now, it looks like, if you look to this model, of course, now it looks like total mess, yes, lot of blocks, total nightmare. But if you, that's why I was trying to draw the picture at the beginning, because actually this is just a PLL, which has input connected from the bandpass and output goes back to this multiplier, and that's it, nothing else, yes. And now we should be able to run it and it should work, yes. Okay, we will save because it could some funny crashes or something like this. Okay, just we say that we will update the version, yes, to 2020. And okay, now we will run. So now we will have a problem. This is a vector signal. So, okay, the problem is that here we have 20,000 samples and PLL will not work with 20,000 samples. That's why, yes, and also we connected to the wrong point, by the way, because we will need this real. Okay, what I will do, I will just cut this out. What? Why it does like this? Ah. Oh, so stupid. Okay, we will. Okay, how to move this part? Just one by one. And I paste this cutted block here because we will need the real part. This is the first thing which we have to do. Another thing which we have to do, we will have to serialize the signal. So 20,000 samples will not work with the PLL. What is this? Some kind of okay. We will put some unbuffer block, which will serialize the signal. Put unbuffer. Lab work will have this picture, so it's not a big deal. And it will be actually a little bit simpler because we have a lot of scopes now, and we will need unbuffer here. And then, of course, after the PLL, we need buffer because sound device will work very bad if you do use some scalar signals. That's why we need buffer block here, and maybe we will put it after the scopes to not have different signals in the inputs of the spectrum analyzer. So we will go to the library and use buffer and put this buffer here. So this is because we need scalar, not 20,000, but one, and then this buffer could be again. So this is not, but here you should again put, no, any number, but quite big, like 20,000 will be okay. So it will collect 20,000 samples and then shut them in one step to the sample rate converter. And it works much better if it puts one by one those samples here. So it will be like the real bottleneck in the model. So this unbuffer buffer, but PLL cannot work with packets of samples. It needs samples one by one. That's why we put this I will put the names. It is not a good idea by default hide the names. Maybe it could be configured that it will not do it, because for you it's important to see what block is it. Yes, it's unbuffer and buffer block. Now hopefully everything is fixed. Okay, now it's different. Okay, there is a somewhere time and frequency mixed. This is sample time. Okay, I think I just made mistake in the init script. I believe that I put the frequency with time messed. Just let's look here. Yes, this is the time, so it's 1 divided by 2040 kilohertz. I have rerun it. It will recalculate the coefficients. Okay, this is a warning. Error. Okay, this is like some parameters of the spectrum analyzer 1. This is I think this is PLL spectrum analyzer. Okay, let's remove it at all. Not a big deal. Scope we will leave for a while, because if something goes wrong, we need to have. Okay, actually it's running, and so if we, for example, run simulation and it seems like one of the signals is 0, yes, it's something is really bad, because if we see here, this yellow is 0, and view style, the yellow signal is coming from the sum. Oh, okay, that means this PLL control signal. Okay, this is very strange that this scope have now different layout. Because this is a signal at the input of okay, it doesn't restore view. Time must be 200 divided by F2. And this is not now 200. I believe this is totally different value. This is our modulated signal. And this is signal generated by the PLL at the bottom. And well, because the signal is not clear at all, the PLL doesn't synchronize. Yes, but if we look to the spectrum, it also not that nice. It's interesting that it shows. Oh, so you see it's so glitchy. I think it would work if we could manage this problem with too weak signal. And of course, if I put the antenna back, because I have heard from the students that this setup requires some kind of antenna which is on the wire. Because if you have antennas staying apart few centimeters, I will just take this antenna maybe and connect it to the Pluto and put some meters away. Then this problem of too close antennas, I have heard about it, that if you have, because in the spring we was working at home, yes, and people had these SDRs at home, and they of course had only one. And they did this, what I'm doing now, they have this transmitter in the same model as a receiver. But as you see now, the power must be tweaked. Why it's such jumping here? It looks like have some automatic gain control. It's doing some bad thing, but this is not automatic gain control. Like, okay, let's remove the. Okay, let's use here like 50. Here put 0, minimum power of the transmitter. Because we must have here like 45 kilohertz oscillation, but what I see here, it's not far that nice. Here it looks like okay, we have a carrier and 2 5 kilohertz peaks. Here also looks nice. You have this okay, view style. Let's check which signal is. Blue one comes from the unbuffer. No, yellow one comes from unbuffer. That means this is signal, yellow signal is coming from this. This is before demodulation. And from after demodulation, this is the blue one. And here, it looks like exactly opposite. This high frequency signal have this very strong DC component coming. No, okay, yes, this is because we are measuring also because the PLL. No, PLL signal comes here. Spectrum analyzer goes here. But this cannot feed back. What's here? What on this scope? After the demodulation. Okay, there is some strange things going on regarding, I think it's related to the overload. Okay, minus 30. minus 20. Looks strange, like you have a frequency offset. Okay, yes, we have this frequency offset. Yes, of course. It's my fault because we have this 40 kilohertz offset, which I forgot about, yes? In the receiver, we have to put 43 plus or minus 40 kilohertz, yes? Otherwise, we will have this problem, plus 40 kilohertz or minus 40 kilohertz. But you will need this, otherwise, you will not be in the center. Oh, now it's nice, you see. Okay, this is kind of little bit jumping. I don't know what is the reason of this jumping, but now it's okay. You see, this is our AM transmission. This is yellow. It's centered at 40 kilohertz. It has only 3 components because we are transmitting sinusoid. This is our sideband, upper and lower sideband. And this blue is after the demodulation. This is like, I will need this DC blocker as well here. And this is after the demodulation. And this is a double frequency component, which will be filtered out. Yes, because we will need as well here, as I already said, we need this low pass filter and DC blocker, by the way. So actually, we look for the low pass filter. Okay, we will put it here. And this low pass filter must be like, you can use even this ER filter. Important is it must be impulse sample rate must be inherited. It is 240 kilohertz. So, and now we have pass bandage frequency. It could be like this, or a little bit higher, because in fact we have audio until 20 kilohertz, and we could use like higher number, like for example here could be 15 to 20. And we could not be so strict at this ripple. We could increase it much higher, let's say to 5.5 dB. And this could be also smaller. It will not, if you do not change, it's okay as well. But if I do this, and this is code generation, it will not put such high requirements. So now if we look to filter response, okay, we will just say that this is 240 kilohertz, apply. Now it will design the filter. You see, it's like not very good filter, but it will filter the audio frequencies. And if you view the coefficients, it is like not very complex filter, like four sections with like 5 coefficients. It's not very highly intensive in terms of calculations. And what we will do else, we put DC blocker here. Also, just look for the DC something, and here is DC blocker, and you will put it here. Because you see in the spectrum, we have this DC component, which is very high, and this is not good for the sound. Yes, because it's sound, This is a like direct current coming to the sound card. Of course, it will be blocked by the hardware, but it's good to not even propagate it to here. And this, I think, could be perfect design. Let's check if we have this. Yes, DC blocker in this lab work description we don't have, but it could be a good idea to have this. Okay, now it gets synchronized. Once it's synchronized, I think this is because of the not well adjusted times of the buffers of something like this. We have this jumping behavior, and it will not be that nice. We should maybe somehow calculate number of samples correctly to not this like jumping all this stuff. And okay, I think you are already tired. I hope that you are listening to me. Is anyone listening to me now? Okay. Okay, guys, so look to the recording next time, because you are not listening to me, and hopefully you will be successful with the laboratory work. So
Yes, but I have one doubt, like whether our version will be compatible to the Matlab AnyDesk version. I mean, I am using 2019. I built PLL in it, but the air modulation was done on Matlab 2018.
Okay, you can do it by, if you have a model, let's say this model, and you will need to go to lower version. You have these options like save as. Okay, because it's still running, I have to stop it. You have this save, and this is previous version. Look here, yes?
Yes.
And you can, okay, I have to save, and then it's save to previous version. And then you can select older versions of the Matlab.
Okay.
And then we'll export to this older version. And then you will open, and then you can send to the desktop and to any desk, and then you can use it. Yes, this is also manual way to go back. Of course, if you go to very old versions, I believe there will be some problems, but it works okay. It just because many students had much older versions, and they moved forward and back, and then it worked quite good.
Okay.
So I think we will next time meet, and we will try to do this on the AnyDesk, but it's good that we will have this video, and maybe you could try by yourself. And anyway, because if we would spend this time at the beginning of the next lecture, it would be not good for you and for me, because I have now remember what have to be done. But actually, this is like mix of lab 3 and lab.
Okay, so which model should we build? Like my model is with 1 VCO, not 2. So should I reconfigure it to
Yes, we need
2
this
VCO?
VCO, because last time we discovered this, because actually, of course, you can use this derivative as well. Yes, and in the
Yes.
what I'm looking in the lab work description, we still have this derivative. But seems that second VCO works much better than this derivative.
Okay.
And, you can use derivative, you can use second VCO, and this is up to you. because
Okay, boss.
last time we was using derivative and derivative was working as well, but because of this nonlinear distortions for derivative is much higher, I believe that it will make more difficult to tune, and maybe it makes some decreased quality. However, I think in our case, it's not big deal. So you can use also, because actually in this place, we have this, okay, we have this discrete time derivative connected to this first VCO, and then it goes out. So instead of this scheme, you can use this scheme with second VCO, but you can also not use this second VCO, but connect this derivative at the output of the first, because this derivative does approximately the same as this second VCO, but at much lower cost computational. But we last time discovered that quality is not that nice in this case. Okay, what is this?
Okay.
So why it's so annoying? Okay, so guys, sorry for the delay, but we had to finish, and now it's more or less working. We have, of course, here could be some better connections. For example, this spectrum analyzer could be better connected to this place after all this stuff, because then we will see much clearer signal. But on the other hand, we will not see this DC component and all this stuff, which is also, but also we will have problem in this case, because there is buffer block in the middle, and they will have different signal dimensions, and then it could be problem for this spectrum analyzer. So let's leave it at this. So, okay, any other questions?
No, professor.
Okay, then I see you next week, and we will do lab work on this funny stuff. Okay,
Okay.
so